let's summarize where we've come to in our solution of the one-dimensional Schrodinger equation. We've seen two types of solutions. We've got free particle solutions, which lead to scattering states. And the characteristics of the free particle solutions are they're not normalizable, they're labeled by continuous variable k, they're actually not physical, they give you imaginary results, and the general solution is a linear combination written as an integral of dk. So we saw that the example that we did for that was the free particle. On the other hand, we have, so those are scattering states. On the other hand, problems like the harmonic oscillator and the infinite well yielded bound states. And the characteristics of bound states are they're normalizable, they're labeled by a discrete index instead of a continuous one, usually n. We can physically realize them. And the general solution is a linear combination of sums over n. And so those are kind of the two choices, although we're going to see some instances where certain potentials give us both bound and scattering states. Now, let's have a look at this first diagram. So here we have a diagram of plotting potential versus x, and we have a total energy of E, a constant total energy, and we look at the trajectory of in this case, a little cart moving through this trajectory. Notice that classically we would look at these 2 points here and here as our classical turning points. That's where the direction of motion would change. And this is the way a bound state would look. So this is your classical bound state in between these two regions. The particle is bound. Now, for regions where the potential is greater than E, we say that the particle could not escape. The particle is basically stuck in a potential well, so to speak. It may rock back and forth between the two turning points, whatever the case may be. And as I say, we call these guys bound states. On the other hand, though, in the scattering case, like for example the free particle, there are a couple of ways this can come about. In this case, E exceeds the potential on either one or both sides of the motion. And in the case where E is greater than Vx on one or both sides, the particle comes in from infinity, slows down, or speeds up under the influence of the potential, and then it heads back to infinity. That's what we call a scattering state. So the general rule we can adopt is the following. If E is less than V at infinity and minus infinity, we have a bound state. If E is greater than V at infinity or minus infinity, we have a scattering state. That's another rule we're going to use. Furthermore, since V is usually 0 at infinity and plus infinity and minus infinity, it's even simpler. We can just say when E is less than 0, we have a bound state. When E is greater than 0, we have a scattering state. So since V approaches infinity at x equals plus minus infinity for the harmonic oscillator and the infinite square well, all we get in that case are bound states. V is equal to 0 for the free particle, so the only thing that we get for the free particle would be scattering states. But there are some examples where you might see both. Or in this case, look at this example. A classical particle would be in a bound state between these two places, these two turning points. But as it will turn out, as we'll see, a quantum particle can actually tunnel through the barrier in situations like this. And we'll show you examples of this later on. So, as I mentioned, we have some types of potentials that yield both bound and scattering states. And the one that we want to look at, first off, is the delta function potential. So let's do that. We define a delta function potential, that is to say a direct delta function, which is not really a function, strictly speaking, according to the mathematicians. Delta of x is equal to 0 if x is unequal to 0, and is equal to infinity if x is equal to 0. Such that the integral of from minus infinity to infinity of delta x dx is equal to 1. So that is to say, we've mentioned this before, you can imagine essentially an infinitely high object that's infinitesimally thin, such that when you multiply the length and the width, you would have an area of 1. And this is, of course, these things don't exist in nature. However, there are things in nature that very much approximate delta functions. And so the delta function potential is extremely useful in everything from electronics and solid state devices and other things as well. But it's worth spending a little bit of time on the delta function, talking about some of its properties. For example, f of x times delta x minus a is equal to f of a delta of x minus a, since the delta function is 0 unless x is equal to a. More importantly, probably this is the one that you use the most, everything from solid state devices to field theory. F of x, integral of f of x delta of x minus a dx is equal to f of a times minus infinity to infinity delta of x minus a dx. And of course, this is going to be equal to 1. And so that gives me just simply f of a. So the delta function in an integral is used to pick out the value of f of x at point A. It's a very, very useful device. Let's consider now a delta function potential. Suppose we let v of x equal minus delta of x. Let's make it, put a constant in front, let's say minus alpha delta of x. Our Schrodinger equation becomes partial with respect to psi minus alpha delta of x. Psi is equal to e psi. And I'm expecting to see both bound and scattering states with a potential such as this. Let's look at the bound states first. So in this case, E is less than 0, and it's 1. If x is less than 0, v of x is equal to 0. And therefore, my Schrodinger equation looks like this. Second derivative of psi with respect to x is equal to minus 2me divided by h bar squared psi. And I'm going to let that equal minus 2me over h bar squared. I'm going to write as kappa squared psi, where I define kappa as simply the square root of minus 2me divided by h bar. General solution to this, obviously, psi of x can be written as a e to the minus kappa x plus b e to the plus kappa x. Now, as x approaches, if x approaches minus infinity, my first term is going to blow up. Therefore, I have to require that a is equal to 0, and I'm left only with the second term. So for the case where x is less than 0, what this all amounts to is psi of x is equal to b e to the plus kappa x. On the other hand, suppose e is greater than 0, v of x is equal to 0. I should say for x greater than 0, not e greater than 0. And this should be x less than 0, sorry. In that case, second derivative of psi with respect to x is equal to minus 2m d psi over h bar squared. And I'm going to let that equal k squared psi instead of kappa. My general solution, psi of x, will be equal to f e to the minus kx plus g e to the kx. Same reason as before, we've got to require that g is equal to 0, because as x goes to infinity, this term will blow up. We can't have that. So psi of x is equal to f e to the minus kx. Now what we've got to do is we're going to join these two solutions at x equals 0. They have to be the same solution at x equals 0, because for x less than 0, we have this solution. For x greater than 0, we have this solution. So we're going to use standard boundary conditions. 1, psi is always continuous. And 2, d psi dx is also continuous, except, obviously, at x equals 0. We're going to be a little bit careful there. So immediately we recognize in order for psi to be continuous at x equals 0, it has to be that f is equal to b. d psi dx, of course, is going to be discontinuous at x equals 0 because v of x is infinite there. Well, that may be the case, but we can sort of do a workaround here to accomplish what we need to near x equals 0. So what we're going to do is do this. We're going to integrate the Schrodinger equation from minus epsilon to plus epsilon, and then take the limit as epsilon approaches 0. So, and this is going to give me, I'm going to use 3 terms here. Let's do it up here. And this h bar squared over 2m, integral from minus epsilon to epsilon, second derivative of psi with respect to x, dx, plus my second term, minus epsilon to epsilon, v of x, psi of x, dx, and the third term, e times the integral of psi of x dx from minus epsilon to epsilon. Let's examine the three integrals separately. Integral number 3, fairly simple. As epsilon goes to 0, we take the limit, epsilon goes to 0, of e times psi of x dx. Well, this will turn out to be 0, because what we're doing is we're getting an area which is the product of a finite height and 0 width. So that's easy enough. That third integral then will drop out. That would be 0. Let's examine the first integral. So integral 1, minus h bar squared over 2m, integral minus epsilon to epsilon, second derivative of psi with respect to x. I'm going to write that as minus h bar squared over 2m d psi dx evaluated between minus epsilon, because if I integrate the second derivative, I get the first derivative. And I'm going to write this as minus h bar squared over 2m delta in parentheses d psi dx. So if I equate, because the third integral is 0, if I equate integral 1 and integral 2, look what I get. Let's do it over here. I'm going to get delta d psi dx is equal to 2m over h bar squared, limit as epsilon approaches 0, minus epsilon to epsilon, d of x, psi of x, dx. Now, since v of x in our case is minus alpha delta of x, the integral minus epsilon to epsilon alpha delta of x dx is just going to be equal to minus alpha psi of 0. Because delta of x is going to vanish for all other values other than 0. Forgot a psi of x, psi of x dx. Okay. So I'm going to write then delta of d psi dx is equal to minus 2m alpha divided by h bar squared psi of 0. So for psi of x equal to b e to the kappa x, that's going to be for x less than or equal to 0, and psi of x is equal to b e to the minus kappa x for x greater than or equal to 0. d psi dx is going to be b kappa e to the minus kappa x and therefore d psi dx is equal to b times kappa at x equals 0. By the same token, d psi dx is equal to minus b kappa e to the minus kappa x for x greater than or equal to 0. Therefore, d psi dx is equal to minus b times kappa. at x equals 0. What that all means, so I go to the left-hand side, then delta of d psi dx is equal to minus 2 b kappa. And therefore, psi of 0 must equal b. And minus 2m alpha b over h bar squared is equal to minus 2b kappa, which means kappa is equal to m alpha over h bar squared. So my allowed energy then is minus h bar squared kappa squared over 2m, or minus m alpha squared divided by 2 h bar squared. So that is my energy eigenvalue for the bound state of the delta function potential. We're not done yet. Let's normalize psi. So to normalize psi, integral minus infinity to infinity psi of x squared dx is equal to 2 times b squared minus infinity to infinity e to the minus 2 kappa x dx, which is b squared over kappa. And of course, that's got to be equal to 1 if it's normalized. That means b, my coefficient b, is equal to plus or minus the square root of kappa, which of course is plus or minus the square root of m alpha divided by h bar. We can just choose the positive root. We don't have to, but we'll just choose the positive root, and we'll get psi of x then, putting in our normalization, is square root of m alpha over h bar, e to the minus m alpha x divided by h bar squared. That's my energy, that's my eigenfunction. My eigenvalue, e, once again, is minus m alpha squared divided by 2 h bar squared. So this is my one bound state, psi of x, and then of course my energy eigenvalue that corresponds to that bound state, e, is minus m alpha squared divided by 2 h bar squared. Great, that's a good start. But what about the scattering states? Let's see if we can get a start on that this time before we have to quit. We're going to use an approach that's not all that different from what we did before. So in this case, e is greater than 0. So for x less than 0, I can write my Schrodinger equation in the following way. Psi, I'm going to write that as minus k squared psi, where I'm defining k by square root 2me over h bar. My general solution, psi of x is equal to a e to the I kx plus b e to the minus I kx for x greater than 0. In this case, both terms are allowed because neither will diverge at x equal to plus infinity. So that's for x less than 0. For x greater than 0, we have psi of x is equal to f e to the I kx plus g e to the minus I kx. And since psi of x is continuous at x equals 0, it must be that f plus g is equal to a plus b. In addition, if I take the derivative, d psi dx is equal to ik times a e to the ikx plus b e to the minus ikx. D psi dx for the second term is equal to ik f e to the ikx plus g e to the minus ikx, or d psi dx is equal to ik a minus b, we'll call it from the minus direction. D psi dx in the plus direction is equal to ik f minus g. Therefore, delta d psi dx would be equal to ik f minus g minus a plus b.
Less than a minute.
We're going to pick this up in our next lecture. Thank you.